Hello and welcome back to Chopstick Maths Differential Equation, exercise 10, sum number 1. The given differential equation is d square minus 2d plus 1 into y is equal to x sin x. Now the given differential equation is of the type f of d into y is equal to capital X, where capital X is x into v, where v is any function of x. So we can write f of d into y is equal to x into v. Now the solution to this differential equation is y is equal to the complementary function plus the particular integral. That is the solution has two parts. So first let us calculate the complementary function. And this is very easy. This is calculated by equating f of d is equal to 0. That is d square minus 2d plus 1 is equal to 0, and to find the roots. Now this is also called as the auxiliary equation. So let us find the roots of this equation. Factorizing this, we get d minus 1 into d minus 1 is equal to 0. So the roots are 1, 1. So we can see that the roots are rational and repeated. Therefore the complementary function would be c1 plus c2x into e raised to x. Now let us find out the particular integral. Now the particular integral is pi is equal to 1 upon f of d into x into v, where v is equal to sin x. Therefore, if the capital X is of this type, that is x into v, then we have to write pi in this particular form, that is x minus 1 upon f of d into f prime d, that is the first derivative of d, into 1 upon f of d into v. So now we can write pi of this differential equation is 1 upon d square minus 2d plus 1 into x sin x. Now since our capital X is of this type, x into v, where v is sin x, that is x sin x, so we will write this pi in this particular form. So pi is equal to x minus 1 upon f of d, that is d square minus 2d plus 1 into f prime d, that is the derivative of f of d. So derivative of d square is 2d, derivative of minus 2d is minus 2, and derivative of 1 is 0. So this would be 2d minus 2 into 1 upon f of d into v, that is 1 upon d square minus 2d plus 1 into sin x. Now let us start from the extreme right. Now this is of the type 1 upon d square minus 2d plus 1 into sin x. Now here if you see, this is a function of d square, and here a is 1. So we'll have to substitute d square as minus 1 square. So we get 1 upon minus 1 square minus 2d plus 1 into sin x. Therefore, pi is equal to x minus 1 upon d square minus 2d plus 1 into 2d minus 2 into 1 upon minus 1 square minus 2d plus 1 into sin x. So pi will be x minus 1 upon d square minus 2d plus 1 into, taking out 2 common, 2 into bracket d minus 1 into, here minus 1 and plus 1 would cancel. So this would be 1 upon minus 2d into sin x. So pi will be equal to x minus 1 upon d square minus 2d plus 1 into 2 into d minus 1 into bracket. Now we can write this as minus 1 upon 2 into 1 upon d sin x. So pi will be equal to x minus 1 upon d square minus 2d plus 1 into 2 into d minus 1 into minus 1 upon 2. As we know, 1 upon d is the integral, so this would be integral of sin x dx. So pi will be equal to x minus 1 upon d square minus 2d plus 1 into 2 into bracket d minus 1 into minus 1 upon 2. Integral of sin x dx is minus cos x. So pi will be equal to x minus 1 upon d square minus 2d plus 1 into 2 into bracket d minus 1 into cos x upon 2. So now we will open the bracket. So pi will be equal to x cos x upon 2 minus 1 upon d square minus 2d plus 1 into 2 into bracket d minus 1 into cos x upon 2. So pi will be equal to x cos x upon 2 minus 1 upon d square minus 2d plus 1. Here 2 and 2 will cancel and we shall open this bracket. So this will be t cos x minus cos x. So pi will be equal to x cos x upon 2 minus 1 upon d square minus 2d plus 1. Now you know capital D is the differential operator. That is the first order derivative of cos x will be minus sin x minus cos x will remain as it is. So this will be minus cos x. Now pi will be x cos x upon 2. Now here in this term you can see we can take out the minus sign common, and once the minus sign common comes outside, minus into minus will make this term positive. So this would be plus sin x plus cos x, as we have taken the full negative sign outside. So this will be sin x plus cos x upon d square minus 2d plus 1. So pi will be equal to x cos x by 2 plus 1 upon d square minus 2d plus 1 into sin x plus 1 upon d square minus 2d plus 1 into cos x. So this would be pi is equal to x cos x by 2 plus, now just focus on this function. Here there is a d square and there is a sin x. So here a is 1. So we can substitute d square as minus 1 square. So this would be plus 1 upon minus 1 square minus 2d plus 1 into sin x plus, similarly here there is a d square and a is 1 over here. So we can write this as plus 1 upon d square can be substituted as minus 1 square. So this would be minus 1 square minus 2d plus 1 into cos x. Pi is equal to x cos x upon 2. Now here minus 1 and plus 1 would cancel. So this would be 1 upon minus 2d into sin x. And also here minus 1 and plus 1 would cancel. So this will be 1 upon minus 2d into cos x. So pi will be equal to x cos x by 2. Now here this term would become negative, plus into minus is minus, and 1 upon 2d we can write it as 1 upon 2 into 1 upon d sin x. This term will become negative because plus into minus is minus, and 1 upon 2d can be written as 1 upon 2 into 1 upon d into cos x. So pi will be equal to x cos x upon 2 minus 1 upon 2, and we know 1 upon 2, 1 upon d is the integral. So this will be integral of sin x dx minus 1 upon 2, and again 1 upon d is the integral. So this would be integral of cos x dx. So pi will be equal to x cos x by 2 minus 1 upon 2 integral of sin x dx is minus cos x minus 1 upon 2 integral of cos x dx is sin x. So pi will be equal to x cos x by 2, minus into minus will be plus. So this will be cos x upon 2 minus sin x upon 2. Now we can take the 1 upon 2 common outside. So pi will be equal to 1 upon 2 into bracket x cos x plus cos x minus sin x. Now this is the complete pi for the differential equation. Now we can write the complete solution. Y is equal to CF plus pi. Y is equal to CF we have already calculated, which is C1 plus C2x into e raised to x, plus pi is 1 upon 2 into x cos x plus cos x minus sin x. That is the complete solution of the given differential equation. Thank you very much.